Okay, welcome to the introduction to organic chemistry. So this is just the introduction. You have a whole other course of organic chemistry, but we're just prepping you for it. So fragrances and odors. So this is the introduction in the textbook. And I used to work for Bath and Body Works and Victoria's Secrets, and it's called Intimate Brands, and they have a lot of fragrances, and we use flavors and fragrances interchangeably. So at least in the fragrance world, that's the same thing. And a lot of the fragrances that you have, they're usually esters, but you have also some that are ketones and aldehydes. But the expensive ones, they're usually esters, and we'll talk about esters later, a certain type of organic molecule. There are also some unpleasant smells like skunks. Skunks have two smelly chemicals in the 2-butan-1-thiol and the 3-methyl-1-butanethiol. So thiols, they put methyl into natural gas to make it smell, and we humans we can smell it in the parts per trillion range for sulfur. And also that we don't like the smell of sulfur either. So you don't want to put something nice like the smell of strawberries into natural gas. Like, oh, I'm gonna smell this for a while. Like, oh, this smells horrible. I'm gonna get out of here. And so you get something you can smell really acutely, very easily, and also that you don't really want to. It's not something like, oh, I could use a nice smell of natural gas or skunk, right? So sulfur we tend to hate. With also these flavors and fragrances, they have to so you can smell them. They have to be volatile. They have to be able to go in the vapor form. But also our noses have to have a receptor form. So the air is about 78% nitrogen, but I don't know what nitrogen smells like because there is no receptor on my nose for nitrogen. So, and that's just because, nor for oxygen either. So, certain things are volatile. Carbon monoxide, carbon dioxide, we can't smell them, but they're certainly volatile. But then other gases like SO2, sulfur dioxide, you can really smell that. That's pretty strong smelling. That we certainly can have receptors on our nose for that. So then, but many of the common smells these are caused by organic molecules. What is an organic molecule? An organic molecule is a molecule that contains carbon. Carbon specifically, that's not a carbonate or carbon monoxide, carbon dioxide. So, but the organic molecules here is a branch of chemistry called organic chemistry, and it's essentially the chemistry of carbon with a few exceptions like the inorganic carbonates and some of the gases like carbon monoxide and carbon dioxide. So all these reactions here with the molecules containing carbon is within the realm of organic chemistry. So here are two other aldehydes, cinnamaldehyde and vanillin, that are the flavors responsible for cinnamon and vanilla. So organic chemistry, I already mentioned this as well. And carbon is a very unique atom. And what is unique about carbon? So it can bond to four other atoms. It's not necessarily unique to carbon. Silicon could do it too, but silicon is also very different than carbon. Unreactive though, so you compare silicon to carbon. Methane here, methane it's reactive, but it's not that reactive. So if you compare silane, SiH4, if you put silane in air in room temperature, it just bursts into flames. It's very reactive. Whereas methane, you need to have quite a bit of activation energy to light it on fire. So that's one difference between carbon and silicon. The other thing, which is really, really unique to carbon, is the fact that it forms chains. Not only chains, but straight chains. So I've done research with carbon and looking at carbon clusters. And if you throw a bunch of carbon atoms into a vacuum chamber and you apply energy to it, they form typically straight chains. If you do that to silicon or germanium, it does not. They form blobs. So silicon, you throw a bunch of silicon in a vacuum chamber, up to about 19 atoms, they form these like football-shaped prolate sort of structures, and then after 19 atoms, they form what's called caged-like or kind of spherical blobs. But if you do that with carbon, you get lots of chains, or chains with chains on them, which is, you can get cyclized compounds too. So it's not carbon doesn't form cyclized compounds, it just really just forms a lot of chains. And these chains are very important for life because Many of our biomolecules have straight chains with them: DNA, RNA, cell membranes, a phospholipid bilayer. If you tried to make a phospholipid bilayer out of silicon, you would just get a blob. And you can form silicon in chains, but you usually have to alternate between silicon and oxygen atoms. But then that bond is too strong, and it wouldn't be easy to break. Where carbon bonds are strong, but they can also break. So they're very versatile as far as engineering and life forming new molecules and different molecules from starting materials. So life as we know it would not be possible without carbon. And I know some people say, oh, you could have silicon-based life, and at least not life as we know it. And especially life, well, maybe if it was a much, much higher temperature, uh, it could work, but certainly not this temperature and this pressure. And with what we have around here, it's just not possible. Carbon also can form single, double, or triple bonds. So and with each other and with other species too. So carbon can single bond, double bond, and triple bond with nitrogen, for instance. And single, double bond with oxygen. It can single, double, triple bond with itself. So it's very versatile. Carbon also can form rings. So, okay, moving on. Let's talk about hydrocarbons. And this is Celebrity Jeopardy question. Celebrity Jeopardy is always fun to watch Jeopardy then because it's always the easy question. What two atoms are in hydrocarbons? And the answer is carbon and hydrogen, and it's in the name, hydrocarbons, hydrogen and carbon. And aliphatic and aromatic. Aliphatic basically means not aromatic. What does aromatic mean? It's besides the fact that it's very smelly, smells good usually, but well, maybe not always. It's a certain type of stability. So 2, 6, 10, the 2n plus 2 numbers, those are the aromatic numbers, and that's something called the Huckel number, and you can learn about that in subsequent classes. So we're not going to talk about it too much here. Hydrocarbons are also insoluble in water. We know this, that gasoline and water do not mix. So gasoline is mostly octane. It's a hydrocarbon. And aliphatic. So this means not the special aromatic ones. These can be saturated or unsaturated. Saturated means single bonds only. So alkanes are all single bonds. And let's talk about fats. Saturated fats. Saturated fats are bad. Why are they bad? Well, they're all single bonded. Usually animal fats, with the exception of coconut oil. Coconuts tend to have saturated fats. But unsaturated means one or more double or triple bonds. So even better, the polyunsaturated, many unsaturated levels of fats. Those are the good fats. So those have lots of double and triple bonds in them. You can have chains or rings with these. Not necessarily, it doesn't necessarily have to be aromatic to have a ring. And they can be straight or branched, meaning that you have, we'll show some pictures soon, of branched hydrocarbons. Aromatic ones, I really briefly mentioned those already. So types of hydrocarbons, you have alkanes, which are saturated, and you have the unsaturated alkenes with one or more double bond, and alkynes with one or more triple bond. So with organic chemistry, there's a hierarchy rule, and the alkyne is bigger than the alkene. So if you have something with 20 double bonds and one triple bond, it's an alkyne, because the triple bond is more important. And the aromatic hydrocarbon, we'll talk about the benzene ring later. And we won't talk about the Huckel numbers, though I already mentioned them. So I already mentioned these alkanes, and these are not the cyclized ones. You can have cyclized hydrocarbons. If you do, it decreases the number of hydrogens. But the general form are the N carbons and the 2N plus 2. N just being a number. And then alkenes, it has 2 less hydrogens, and alkynes has 2 less from the alkenes, and so on. And with these formulas, so molecular formulas, there are kinds of atoms, but they do not show how they're attached. That's just show the number of atoms in each. Structural formulas shows the attachment pattern, and the models give you more about the shape. So here's a structural formula. You can see it shows it's not just C3H8. C3H8 would be the molecular formula. So that's the structural formula, and the condensed formula doesn't show the hydrogen single bonds. Carbon skeleton gets rid of the hydrogens, it just shows you what the carbon's up to, and also the other atoms. Ball and stick model and the space filling ones, those also you can see them moving over on the right, on the bottom moving to the right. They show you a little bit more of the 3D structure. So structural just the shows not only, you already mentioned that, okay, and we've already covered the previous slide. So isomerism, this is the same number of atoms but different connectivity. So that's what a structural isomerism. We have butane here on the left, that's a normal butane, 4 carbons on a straight chain. Now you have isobutane, the isomer of butane, with the CH3 attached to the central carbon. So a central carbon has 3 CH3s attached to it. So that's a different molecule, or 2 different molecules and have different physical properties, even though they have the same number of carbon and hydrogen atoms to them. They're different connectivities. And rotation is not isomerism. So showing these 2 molecules here, these are both normal butane. So butane being 4 carbons. And it just shows that on the right, you're just kind of moving the carbon over. So, I mean, in this picture, you're moving it down 90 degrees, but I guess in a Fisher diagram, that would be about 109 degrees. So Fisher diagram is a projection from the structural formula. So looking at this, though, single bonds, you can bend them around. They're very easy to rotate. Double bonds, though. Double bonds are not easily broken, and we'll talk about them later with cis-trans isomerism. So stereoisomers, these are the same number of atoms, but they're just in a different orientation. Optical isomers, these are mirror images of each other. So these are very different from each other. These are also known as enantiomers from each other. Okay, so if you look at a molecule in carbon chemistry, organic chemistry, it's easy to figure out which molecules are going to be optically active because it's a central carbon that has 4 distinctly different groups on them. And if you look at your right hand, your left hand, there's symmetry with them, but it's a mirror. Your right hand and your left hand are mirror images of each other, or more or less. I know they're not exact, but they are. There is a bit of symmetry within the human body that way. It's mostly symmetric along a mirror image. Same thing for molecules. And if there are 2 molecules, you can see here on that image there, if you can discern the colors, there's 4 different colors attached to the central carbon atom. And the mirror image, it's said to be chiral. And the 2 different chiral molecules are known as enantiomers. And so what's an example one? If you look here at this 3-methylhexane, the 3rd carbon atom there, it has attached to it has a hydrogen atom, a 1 CH3 methyl group, a 2 carbon ethyl group, and a 3 carbon propyl group. So that central atom has 4 different things attached to that. And then because of that, that's a chiral center. And then this is going to be optically active. So what does it mean to be optically active? It means that the molecule can rotate plane polarized light. But this is only if you have a specific concentration. You have to have a higher than normal concentration, well, not higher than 50% of one of the enantiomers. So because if you have the same, it's also known as a racemic, if you have the same amount of each, if the light is bent one way, the other enantiomer will just bend it the other way and nothing will happen. So if you have plane polarized light, so if you take light and you polarize it, a optically active material, a chiral enantiomer, for instance, will rotate plane polarized light. And so dextrorotary means it rotates light to the left, and levorotary means it rotates light to the left. So maybe we're not going to, well, if you look to biochemistry, maybe you've heard of dextrose before. Dextrose is glucose. Glucose and dextrose means the same thing. Well, glucose is dextrorotary. It rotates light to the right. So that's why we call it dextrose. And also amino acids, they always say L, something you say like L-lysine. Why are you calling it L? Why are amino acids in the human body L? Because all of the amino acids in the human body are levorotatory. So meaning that it rotates plane polarized light to the left. So if you so that's one thing with biologically active things. They tend to be chiral and they tend to be the same actually. So for all things, so all sugars tend to be right-handed, well dextrorotary, and all amino acids for life here on Earth tend to be levorotary. And I already mentioned this. If you have a mixture, it's called racemic. And if you have a racemic mixture, it looks like nothing happens because whatever you bend to the right, the other thing bends to the left, and it seems like nothing happens. But if you have an excess of one or the other, you will get something that's optically active. And with enantiomers, though, a lot of biomolecules have, we're very site specific. So enzyme actions, they only work in specific ways. So that's why we tend to stick with at least life here on Earth tends to form one enantiomer over the other. And okay, so look at this question here. Which one is going to have optical isomerism? So it means you have to have a carbon with 4 different things on it. So if you look at A, carbon, there's only one central carbon, has a chlorine, a bromine, and there's 2 hydrogens. There's not 4 things. The hydrogen's the same. So now if you look at B, if you look at the first carbon to the left, it has a bromine, a chlorine, a hydrogen, and then has a CH3. That's 4 different things. So B is going to be optically active, or at least it's going to have enantiomers. So now if you look at C, the first carbon to the left has 2 hydrogens on it, so that's not 4 separate things. Same thing with the second carbon has 2 hydrogens, not 4 separate things. And then if you look at D, the first carbon on the left has 2 hydrogens and the second carbon has 2 chlorines. So you're not having any carbons with 4 specific things on it. So that's the only one that has it. So, I mentioned the saturated hydrocarbons. They're all single bonds, and this is known as alkane. So, alkanes, I already mentioned everything on this slide. Now, let's look at the physical properties of N, normal alkanes. Normal in chemistry class means straight chain. Going up, methane, ethane, propane, so 1 carbon, 2 carbon, 3 carbon, and you can see the boiling points. As it gets heavier, the boiling point goes up. Why is that? Because of the dispersion forces. So bigger molecule means more dispersion forces, more attractiveness. And you get up to normal octane with a boiling point of 125 degrees Celsius. And compare that to water. Octane is over 100 grams per mole, and water is 18 grams per mole. So it shows you about water from previous chapters. Water has the 2 hydrogen bonds, which gives it its much higher than normal boiling point versus something that doesn't have the hydrogen bond network. But we're not talking about hydrogen bonds. We're talking about organic chemistry. But I like to keep your brains and footed in what you learned before. So, and I already mentioned that this dispersion force is less dense than water. So in gravity, they float. So if you mix gasoline and motor oil with water, the hydrocarbons float to the top. And it's not because they hate water. Actually, they love water. They like water more than each other. They're attracted to that negative end or the positive end of water. But water, get out of my way, you big organic molecule, and pushes it out of the way. And then by gravity, it settles up top. So water is actually a very exclusive mean molecule. So here's normal alkanes. Number 1 is methane, 2 ethane, 3 propane, 4 butane, 5 pentane. Come on, that's next. 6 hexane, 7 heptane, 8 octane, 9 nonane, and 10 decane. So just so you can hear the words saying. And what do we use hydrocarbon for? Mostly fuels, right? Not surprisingly. So carbons 1 to 4, we use these as gas. So methane, propane we use quite a bit for burning. Butane you can use for cooking fuel as well. Also for lighters, use butane. 5 to 7, sometimes these are referred to as petroleum ethers as well. And you can put it in gasoline, like the places that are really cold, like Alaska. They sometimes add additives to gasoline to make it more volatile in the wintertime. What are they adding? They're adding these carbons that are 5 to 7 uh, um, chain lengths. Interesting, actually, they use pentane for. They use that in the self-foaming um, shaving cream. So if you're wondering how some of those technologies, like the self-forming shaving cream, actually they use pentane for that. So there's lots of weird applications. Lighter hydrocarbons. Lighter means smaller in mass. Gasoline also tend to be more branched in gasoline. A little bit longer, we have jet fuel. Even longer, diesel fuel, lubricants. So like motor oil, and also you can use the kind of heavier heating oil. Something like bunker fuel is kind of in the bunker is also not very purified. There's a lot of sulfur in it. And even heavier, you have solids, so paraffin wax, also asphalt. So asphalt is actually a hydrocarbon. What we make a lot of our roads out of is the bottom part of the distillation column. So naming them, you look for, starting, we're going to start with alkanes. You look for the longest carbon atom, our carbon chain, and then you add the number of the atoms, and then ANE. And then you start to name the stuff along the side. So these are all simple ones: methane, ethane, propane. But you get longer, you can start getting branches. So and the prefixes. So I mentioned these before. And here are alkyl groups. So alkyl groups, so so the alkane, and they just have the YL at the end with a number. And so you can have so iso was it's actually a common name. Iso means that it's just the second last carbon has a methyl group on it. That's what the iso means. And the well, I won't go into the history of that. I could talk stories about chemistry and naming things, but this is actually it's kind of considered more of a common name. So, but when you name them, you find the longest carbon chain, and then you add what's next to it. So for this one here, and highlighted in yellow, there are 5 carbons. So this is pentane, but so remember, organic chemistry is a hierarchy. And you try to get the lowest number, but in this case, the carbon is in the center. So the third carbon atom here has a 2-carbon chain. A 2-carbon chain is known as an ethyl group. So this would be 3-ethyl pentane. So, and if you have more than one group, you have di, tri, tetra. So and alphabetizing doesn't matter. Okay, so unsaturated double bonds, you use ENE for the ene. And okay, for okay, so and okay, oh, the trigonal planar geometry on carbon, it's flat, so that's talking about the geometry around it. So that's more for when you play with models. I already mentioned polyunsaturated. Ooh, ethylene, even though I'm using the common name, ethylene. So maybe you smelled bananas. There was something, I remember when I lived in Honolulu, there was this place called the Health Bar, and they like to make banana bread. And whenever you walked in, you get smacked across the face by the smell of ethylene, because they had a bunch of bananas that they just let sit out in there. And as fruit is ripening, it releases ethylene. Ethylene also makes fruit ripen faster. It's called an autocatalytic reaction. And so that's why if you want to get fruit to ripen faster, what do? You place it into a bag. And that's because it traps in the ethylene, which makes it ripen faster. This is, well, the most common use for this is to make polyethylene, a very common plastic. So here are the alkenes. They're just like the alkanes, and except they have the ENE at the end. And notice with here you get to butene, you have the carbon. You have 1. It tells you where the double bond is. So 2-butene would be they would be between the second and third carbon atom for that. And triple bonds, so similar to double bonds, but you have yne, Y-N-E at the end of it. So ethylene, also known as acetylene. I never referred to ethine. It's acetylene. Acetylene here, ethine, has the triple bond, and then you can see it's after you get past 3 carbon atoms, you indicate the number where the triple bond is in the name. It's 1-butyne versus 2-butyne. Okay, so the formulas for 3 non-cyclic hydrocarbons listed below. Which one of these is an alkene? It's the N hydrogen 2N. So the only one that fits that is C. So A is actually an alkane. B, it's not really clear what that is. There's a couple options it could be. C, though, C, if it's not cyclic, is an alkene. Okay. Acetylene is what's used in acetylene. It's in welding torches, and it's pretty strong stuff. So, okay, alkenes and alkynes are named the same way, except for the ending, and well, there you go. I don't have to read the slide. You can read it yourself. Geometric isomerization. So now we get to double bonds. These do not freely rotate. Single bonds, especially at this temperature and pressure. So single bonds may not really rotate that freely, close to absolute zero, but at this temperature and pressure, they do. So single bonds, I mean. So double bonds, though, it takes quite a bit of energy to break them. And if you have the same group, so at least the higher value, the book doesn't really go into this, but there's the higher value group. Here it's usually pretty obvious, but it's the higher value group. If it's on the same side of the bond, that's known as cis. If it's opposite side, it's known as trans. So here for dichloroethane, so if you look at this, so dichloroethane, if you have you can have 1,1 dichloroethane. That means the chlorines would be on the first carbon, just 2 of them. But the opposite here, so they're on opposite carbon atoms, and you can have them on the same side or opposite sides. And what's the importance of this? Well, the trans is nonpolar, whereas the cis is polar. So there's a great deal of physical properties different between these two atoms. And which one's more stable? Actually, the trans is more stable because you can see the chlorine, the one on the left, that electron cloud is really pushed up against it. So it would tend to primarily form the trans, but they can form both. Where have you used cis and trans before? Maybe you've heard of trans fatty acids. Fatty acids tend to be cis. So the unsaturated fatty acids, they have the bonds tend to be cis. And then hydrogenated vegetable oils, how do you make margarine? You take a vegetable oil, you heat it, and you add acid to it, and then it makes margarine. It also makes trans fatty acids because if you have a triple bond, it'll form, and tends to form more trans than cis, actually, because as mentioned before, trans is actually lower energy. So if you ever heard the trans fats are bad, and this is where the trans fats means. It means it's not cis fats. Cis fats are good. So, and I mentioned before, the physical properties are going to be different. And why is the melting point and boiling point higher for cis? Because it's polar bond. So some hydrocarbon reactions. Combustions. Combustion we use quite a bit for hydrocarbon reactions. That's where we get most of our energy from. So not just electricity, but also fuel for airplanes and automobiles. So we burn it. And here's a couple, and I don't want to go too far into some of these reactions. You will learn about these in organic chemistry. And you can have halogen substitution. So you can use heat or UV light. UV light can break bonds. And so for instance, methane plus chlorine can form methylene chloride, so chloromethane sometimes, no, I'm sorry, that's not methylene chloride, chloromethane methylene chloride. I'm sorry, it's CH2Cl2. I beg your pardon there. So chloromethane there, and hydrochloric acid. So that's the general formula down there. So addition. So you can add hydrogen across the bond. So you can use alkenes or alkynes, turn them to alkanes, and usually use a catalyst. The catalyst is usually it's usually platinum. Platinum, palladium is oftentimes used. You can use other expensive catalysts like rhodium as well, but platinum and or palladium is usually the catalyst that they use for this. And hydrohalogenation, so adding that. This is usually when you add it across a double triple bond. Oh, we already mentioned halogenation, so hydrohalogenization. So that's adding one of the strong acids typically. So for instance, adding chlorine across, ethylene here plus chlorine makes 1,2-dichloroethane. And then you have propene here with hydrogen, usually over a platinum palladium catalyst, you get propane. And okay, we mentioned before about aromatics, so here I am talking about aromatics. Has the benzene ring, and the whole thing with the benzene ring is it's got a special type of stability. So it has an alternating single and double bonds. If you have 2, 6, 10, and then plus 4 after that, these can form what are called the aromatic compounds, and they have a special type of stability with them. So they're stronger than normal stability. And here the benzene ring, they're interchangeable, and then the molecular orbitals of that are very particular. So I mentioned a little bit before when we talked about molecular orbital theory in the previous semester. So you're naming them, and you just, if you have a halogen, just end it to O. So chlorine to chlorobenzene, and you can have some common one, ethylbenzene and bromobenzene. So there are also, oh, and if you have a benzene ring in a molecule, you also refer to that too as a phenyl group. So here you have heptane, and then you have the phenyl group on the third carbon. You pick the carbon atom closest to the end. So this would not, for instance, would not be 1, 2, 3, 4. It would not be 5-phenylheptane because 3 is a smaller number than 5. Now, what do you do here with hexane? Is this going to be 3-phenyl 5-hexane? No, the alkane has higher priority. So the hexene has it on the first carbon, the ene. Alkane is defined as an alkane. I'm sorry, alkene. I'll define as an alkene on the first carbon atom, and then you order it then subsequently that way. So other ways you can use the number. I use tend to use the ortho, meta, and para. That's going to talk about later, but this is the official one. So and you mentioned in the groups. So the halogen has priority over the alkane. So you call the number 1 position the halogen, and then the number 3 position is the alkane. And then let's say you have 2. Let's say it was 2 chlorines. It says it's in the first molecule on the left. Say it was another chlorine. It would be 1,3-dichlorobenzene, for instance. And then here in bromine is higher priority than the chlorine. Iodine would be higher priority from the bromine, right? So the old people go first. The bigger, fatter molecules go first, right? So you got 1 bromo, 2 chlorobenzene. And you can also use the ortho, meta, and para. So ortho means that you have, it's they're next to each other. Meta means they're one apart, and para means they're opposite ends. And you can learn about the importance of these later when you talk about with benzene. There's lots of types of reactions that tend to form many molecules. They either tend to form in the ortho or para position versus the meta, and you can learn about that when you take organic chemistry. So how about polycyclic? So many of these, so many benzene rings. Naphthalene, I hate the smell of naphthalene, that's mothballs. You can smell that really far away. Anthracene, pyrene, and tetracene. So just letting you know those are there. And some reactions, for instance, you can substitute them with halogens, for instance. So benzene, though, it doesn't really do well with addition reactions. So it's because of the delocalization. But you can rip the hydrogens off. So the carbons are hard to rip off, but the hydrogens are pretty easy to rip off. Okay, so now we're moving on away from benzene, talk about functional groups. So different type of molecules have different functional groups. So, and I'm really teaching organic chemistry right now, is kind of organizing it in terms of naming, and also I'm going to talk about the functional groups. So what we learned about before, so far we've learned about hydrocarbons, and we've had different types. We have alkanes that are all single bonded, alkenes that have one or more double bonds, alkynes that have one or more triple bond, and then the aromatics that have the benzene ring. And now we're going to talk about different types of molecules. And a lot of times hydrocarbons, we'll just refer to it by the general structure R. So R means hydrocarbon coming through. So we'll start off with alcohols. Alcohols has a hydrocarbon with an OH at the end. And then then ether it can have different R groups as well. It doesn't have to be the same, but you have two different hydrocarbons attached to a central oxygen atom, or ethers. Aldehydes have this C double bond OH at the end of it. Well, C double bond O attached to an H with another hydrocarbon group attached to it, and that's an aldehyde. A ketone means you have one or two different types of hydrocarbons attached to a carbon that has a double bond O on it. So that is a ketone. And carboxylic acids have this terminal carbon that has this C double bond O attached to, or carbon double bond O with a carbon OH on it. And this is a carboxylic acid. Esters, instead of a hydrogen, you have another hydrocarbon attached to it. And these esters, these tend to be some of the better smelling and tasting molecules. And you have amines, which you have a nitrogen with one or more carbon attached to it, and these are usually really smelly. So ammonia stinks, and many of these amines are really smelly molecules. I remember working with trimethylamine, and that stuff smells like fish, like a horrible, rotten, stinking fish smell. But once you start seeing some of these names, though, as you're learning organic chemistry, you might start to hear some phrases and even common speech, and you don't even realize you're talking organic chemistry. So amines, maybe you've heard the word amphetamine before, right? So amphetamine is an amine. Even the word vitamin used to mean vital amines. They're not all amines, but many of them are. But the vital amines, and then they found out, like, oh, they're not all amines, so what do I do? And so instead of saying vital amines, we just kind of said fast, vitamin. So vitamin is not necessarily an amine, but originally it meant vital amines. So we're going to start with alcohols. And alcohol is an ethyl group attached with an OH, terminal OH group. And most common one, of course, is ethanol. And this is the stuff that you get in beer, wine, and whatnot. So a proof is double the percentage, and percentage by volume. Gasohol, so gasohol is just a mixture of gasoline and alcohol. So isopropyl alcohol, it's the isopropyl molecule, but you have the alcohol in the central atom. So the propanol has it on the end of the molecule. Isopropanol has it on the middle, so it has the C central carbon with the OH on it, and it's poisonous. You don't want to drink it. I mean, you don't want to drink methanol either. So methanol is way more poisonous than isopropyl alcohol, if you're wondering. But you can get, so methanol is wood alcohol. You can do it by pyrolysis, thermolysis, pyrolysis of wood. It produces methanol, but also produces other things as well. And yeah, methanol, very, very toxic. Okay, but two other common types of alcohols. And how do you name them? The main chain contains the OH, and the chain closest to the end of the OH, and give the ol at the end. So also reaction with alcohols, you can substitute them to form alkyl chlorides, and you can also do what's called an elimination reaction. And so I don't want to talk too much about this stuff, the different types of reactions, because you learn much more about them in much greater detail in organic chemistry. Uh, we're studying more about elimination reactions. Elimination reactions are actually really hard to form in the gas phase. So we're doing some astrochemistry, and one of the things that space does not have a lot of is organic molecules that have double and triple bonds in them. And that's something that really only happens in the liquid phase. So that's one of the questions, like, oh, what other types of life can we have? And you really need to have the solvent. And the solvent, what actually does, it stabilizes the transition state. So the transition state moving to form this elimination reaction, ripping out the water, ripping out the two hydrogen and forming the double or triple bond in an elimination reaction. You really need to have a solvent, so you're not going to see too many double and triple bond molecules being formed in space. So this is one thing where if life is to form in other places, you need to have it in a liquid environment. So you can have simple molecules like alcohols that can form in space, but you're not going to form that many other molecules, these other unsaturated molecules in space. So you can oxidize things. So common oxidizing is sodium dichromate, usually mixed with sulfuric acid is common for oxidizing. But oxidation, one of the definitions of oxidation is to remove hydrogen or to add oxygen. And also our liver does this quite a bit too. So if you have ethanol, you can rip hydrogens off of it to form acetaldehyde, and then you can oxidize it further to form acetic acid. And actually, alcohol poisoning typically is from acetaldehyde. So the CH3CHO. That's really the more toxic thing than alcohol. And alcohols also react with active metals. So meaning like sodium, or in this case potassium. So if you throw methanol into potassium, you form the methoxy ion, and the methoxy ion is a very strong base. It's stronger than hydroxide. So if you really need to have a solvent that has a very, very strong electron donor, you can use methanol then with throw some alkali metal in it and form the methoxy ion. So even stronger than hydroxide as far as a base. So oxidation to the right means you get more lose hydrogen and gain oxygen, and then reduction to the left, you gain hydrogen, lose oxygen. So an alkane, if you react it, you can form an alcohol, and then you can rip hydrogens off to form an aldehyde, and then you gain more oxygen to form a carboxylic acid, is the direction of oxidation. So aldehydes and ketones. So an aldehyde has a carbon double bond O at the end of the molecule. A ketone has it in the middle. So that's the difference between the two. And a lot of them smell good, and some of them don't smell very good at all. Formaldehyde, I don't like the smell of formaldehyde. It's not really that great. And formalin, I still don't like the smell of that. You mix it with water. And so it is slightly carcinogenic. Acetone, I also don't like this. I don't like the way it smells either. It's a nail polish remover. Ugh. Acetone, strong smelling stuff. Smells better than formaldehyde though. Common aldehydes and ketones. So acetaldehyde, I already mentioned that, and propanal. So that's That's the Al is the aldehyde al, and one is the ketone. So acetone is the propanone, the three carbon, and then butanone here next, and then benzaldehyde. So that's a flavor that's in almonds. Almonds also have cyanide in them, so that's another flavoring of almonds. Believe it or not, a cyanide, but benzaldehyde is another one. Other ones, so acetophenone is pistachio, carvone is spearmint, peppermint's different, that's methyl salicylate, so that's an ester. Uh, ionone is raspberries, and muscone is musk. So naming them, I already mentioned that as well, has to have the C double bond O, except for the carboxylic acid. That's a different group. So it's C double bond O without the OH on it. And aldehydes, you give the al, and the ketones, you give the one. And there. And the reactions, so you usually get them from alcohols, and the reduction of you can reduce them as well to form an alcohol. And additions occur, they occur towards the double bond C carbon double bond O due to its polarity, and it's because it draws the electron clouds of that towards that carbon, actually the oxygen. It draws the electron. The oxygen is like a vacuum cleaner. It's drawing all that electron density to itself, and it can create that end of the molecule to be a bit more reactive. So other ones, so you have polar molecules add across the C double bond O with the positive part attaching to the oxygen. So for instance, here you have formaldehyde reacting with hydrogen cyanide in solution to form that molecule there. So, and I already mentioned that the carbonyl group, the oxygen is just drawing all of that. Why is it reactive? It's drawing all the electron density towards the oxygen, and it's weakening those bonds, making them more susceptible on the outside carbons to more isolated attack. It's easier to react. Okay, so moving on to carboxylic acid, it's the carboxylic acid group is always at the end of the molecule, and you give the end oic acid. So although I use acetic acid, it's ethanoic acid. Esters, you name it as if the carboxylic acid, but then you add the alkyl group, and then you name the chain with the O8 ending. So here are, so remember you have the ethanoic acid and acetic acid. I'll use the proper name, ethanoic acid. So ethane, but there's the two carbons, ethanoic acid, and butane, but with the four carbons, butanoic acid. And now you have the ester with the methyl group. So you add the but for 4 and the O8, so butanoate, and then you have the methyl group attached to it, so it's methyl butanoate. And if it's, say you have, now instead of propane, you have the propionic acid. I'm saying it without the ester, propionic acid, but then you have an ethyl group, so it's ethyl propionate. So it's like propionic acid, but now instead of a hydrogen, you have an ethyl group. Just like methyl butanoate, methyl butanoate, I can say it, butanoate. You have, it's like butanoic acid, but you have a methyl group, so it's methyl butanoate. So high carboxylic acid, many of these, and typically if you have a long hydrocarbon chain and you have a carboxylic acid group, it tends to be not water soluble. So a lot of fats, pretty much almost all fats here on Earth tend to be triglycerides. So you have glycerin. It's a triple alcohol. It's 3 carbons with 3 OHs, and then you have a fatty acid attached to it. So you even use the word fatty acid. So it's a carboxylic acid. So most carboxylic acids are not, at least the number of molecules that we know, they tend to be long carbon chains, and they usually are stored in terrestrial life uh, as the 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 glycerin trifatty acid, triglycerin esters, so kind of thing. But here you can get something that has, like citric acid here has 3 carboxylic acid groups on it, so this is water soluble and it tastes sour. These are weak acids, not strong acid. But short chain, so ethanoic acid, well, also formic acid down there, that's toxic. Inside bites and stings. If you drink methanol in terms of formic acid tends to attack your optic nerve, so it can make you go blind. So ethanoic acid, so that's acetic acid vinegar. Citric acid found in citrus fruit. So these are the sour. I've never tasted formic acid before. I've certainly tasted vinegar before and citric acid, but I'd imagine that formic acid would taste sour. And the word formic, that comes from the Latin for ants. So formis, the Latin for ants, and so that's where the formic acid name comes from. And also, if you they call them the formics if you're a fan of Orson Scott Card like I am, if you into that sci-fi series. All right, no more talk about literature. This is science class. Okay, esters. These tend to be they smell good. So ethyl butanate. Or butanoate, sorry, ethyl butanoate. This is the pineapple smell. And butanoic acid, so 4 carbons, but you have an ethyl instead of a hydrogen, so it's ethyl butanate. So good smelling stuff. Condensation reaction. So this is a condensation reaction is a reaction that water is a product. So because things come out, and you can take an acid and an alcohol and you can make an ester. And why do we care? Well, this is how you make diesel fuel, or biodiesel, excuse me. Biodiesel is you have a fatty acid, and how do you make diesel fuel? Or I'm sorry, biodiesel. Diesel fuel you make from oil. Biodiesel, you take something, you take a low value fatty acid. And then you would react with an alcohol, usually methanol or ethanol, more typically methanol, and then you react it with acid. Well, even before that, you take your fat and you throw it into sodium hydroxide. It's called a saponification reaction, and then that rips apart the triglyceride bond to get the fatty acid. So that's how you isolate fatty acids from the triglyceride fat storage, and then you add an alcohol and you mix it with sulfuric acid and you heat it up and then you form an ester. So that's how typically you make biodiesel. And then that ester is then what you throw into your diesel engine. Another one is aspirin. Aspirin is acetylsalicylic acid. Salicylic acid, it's a drug. It's a H1H2 blocker. I'm sorry, COX-1, COX-2 blocker. So COX-1, COX-2, those deal with the stomach, kidneys. Is H1, I'm sorry, H1, I keep saying COX-1, COX-2 is the swelliness sort of thing. So why does aspirin alleviate your ankle sprain? Well, alleviates the pain. It's an anti-inflammatory. It eliminates the COX-2 chemical signal, COX-COX, and it's kind of like the Jedi mind trick. It tells your body there is no pain, there is no injury, there is no need to swell up, and so decreases swelling, decreases your pain. So salicylic acid does that, and but salicylic acid is also pretty tough on your stomach. So Bayer figured out if you add acetic acid to it to form acetylsalicylic acid, then that can give you the benefits of salicylic acid, but without the toughness on your stomach. So that's how you make aspirin. If you're wondering, you mix it up with so salicylic acid you get from trees. Tree bark, and acetic acid from vinegar. You can also use acetic anhydride. It's actually easier to do the acetic anhydride, but it's also more expensive. Another fun reaction you can do here is you can add a methyl group to make methyl salicylate, and that's it's a mint flavored product. It smells really good. Okay, organize from least oxidized to most oxidized. So remember, the most hydrogens is least, and the most oxygens is the most oxidized. So number 3, the propane. This is the most oxidized, and this is the most reduced. And then alcohol is the next one. So you can see it has one hydrogen, and then if you rip off the hydrogen, you have you have the ketone there, and then finally you have the carboxylic acid. Well, in this case, it's an ester. So, if you count the number of hydrogens, so 4-propanol has, well, actually, isopropanol has an oxygen, but also has a hydrogen attached to it, whereas acetone there, one, does not have the hydrogen, so that's more oxidized. So 3, then 4, then 1, and then 2. This is the one that's the most oxidized. It has the most oxygens. So in this case, it's an ester, but it could be also a carboxylic acid. Okay, ether. Moving on, talking about ethers. Ethers have two of the same or different alkyl groups attached to a central oxygen, and the most common one by far for ethers is diethyl ether, because dimethyl ether is it's a gas at room temperature, and same thing with ethyl methyl ether. It's really hard to work with. Diethyl ether though, but it's really flammable and can be quite explosive. So be careful with ethers. And used to be used as a drug. It was the first anesthetic, actually. Used ether and then later chloroform. It boils pretty low. I think around 35 Celsius, does it say? Okay, no, it didn't say. It's pretty low. It's not that hot much. It's around body temperature. So that's one thing about ether. It's can form other explosive compounds. So ether's scary. Okay, so moving on, talking about amines. Amines mean one or more alkyl groups on nitrogen atoms and on ammonia, and these usually, you name the alkyl groups by the ones attached to the nitrogen. So here, the first one, this is ethylamine, and then the second one here, ethylmethylamine. So you have an ethyl group and a methyl group. And like I said, these are really bad smelling, really, really badly smelling. And also not listed in the textbook, you can also get a series of chemicals called quaternary ammonium salts. So if you can get 4 things attached to a amine, you can form a quat or quaternary ammonium salt. And these are typically used for antimicrobial. They can also be used for fabric softeners and detanglers and shampoos and conditioners. But one of the common usages for quat, it's also an amine, but it's quaternary. It's a quaternary amine with usually an alkali counter ion, antimicrobial. So very important, because I'm also talking about this during a pandemic. So okay, so these can react with here's the ammonium salts. That's what I mentioned before. Those are quaternary ammonium salts. We use those for antimicrobial agents. And they can form with carboxylic acids to form amides. And why do we care about amides? Because that's what proteins are. Proteins are polyamides. So an amino acid is a amine with a carboxylic acid attached to it, and then they can turn into chains, and that's what proteins are. They're polyamide proteins. Okay, and remember, this is just an introduction, but I hope you enjoy the introduction to organic chemistry.